Hey guys, so in this video we're going to be talking about how to calculate the area under a curve using an integral and how it actually works. So let's say I have a random function which I'm going to call y equals to f of x, and let's say we want to calculate the area under this curve from some point C to D on the x-axis, right? So essentially we want this area right here. If this were a standard geometric shape, say for example a rectangle of some known length and known width, we could just multiply the length and the width and get the area. But in this case, this is not a standard geometric shape, so we cannot just plug some formula and get a really nice area. So what we want to do, since we're talking about rectangles, is let's divide this area into some rectangles of equal width, which I'm going to call delta x. So the height of the rectangle is essentially going to be the y value at a certain point, right? So, and y is just a function of x, so this height is just going to be f of x. So if I want the area of one rectangle, I just multiply the length, which is fx, times the width, which is delta x. So in this case, we see that we're actually missing quite a few areas. So we're missing the area right here, and right here. So how do we correct it? So what we want to do is, let me draw another figure right here. Let's actually reduce the thickness of the rectangles. So it's going to look something like that. And forgive my bad drawing skills, right? So it's going to look something like that. And we can already see that the area that we're missing, or our error, is getting smaller than it was previously. So essentially, what we want to do is, as delta x goes to 0, that is, as the width is reduced and reduced, the error is essentially going to go to 0. So that is basically the idea of integral. So just adding up individual rectangles would be summing these up, right? So if I do that, if I put a limit as delta x tends to 0, then basically I'm adding tiny little rectangles over this, or I can also represent this as I goes from 0 to some n. These are basically the number of rectangles, and I can put n goes to infinity. So what that means is I'm adding infinitely many rectangles of really small thickness just to complete the area from the point C to the point D. So that is the fundamental idea behind an integral. So how would we do that is, let me again draw our curve, y equals to f of x, and we're going to select a tiny differential area, which is going to be a representative of all these tiny rectangles that we can take. So this is the area that I'm choosing, and the height of this rectangle is still going to be f of x, and this right here, I'm going to call it dx because it is really tiny x, or delta x, right? So the area of this tiny strip here is going to be the length times the width, which is dx. So let me just call it dA, which is the differential area, right? So if I want to find the total area of this whole figure from point C to D, all I need to do is integrate this dA. So integrate fx times dx from C to D. And thus, that is how the formula for area under the curve comes from using integrals. So let's test our knowledge to calculate area under the curve for some function. So let me just erase this right here. And all right, let's do something that is actually known to us to check if what we just derived is correct. So let's say I have the line y equals to x, and I want to calculate the area under this line from the origin, or is x equals to 0, to say x equals to 5, right? So why am I doing this? Is because this is a triangle. And we know the area of a triangle is just going to be 1/2 the breadth, or the base, I'm sorry, times the height, which is, in this case, if this is 5, y equals to x. So this thing is also 5. So the area is just 1/2 times 5 times 5, which is 25/2, which is just 12.5. So let's use the idea of integrals and see if we arrive at the same answer. So for integral, let me choose a tiny strip right here. So this is going to represent my differential area, and my width is going to be dx, and my height is going to be fx, or f of x, or just you can just call it y, because y is still a function of x, right? And the differential area is going to be fx times dx. So I want to integrate this to get the total area from 0 to 5 of fx is just x times dx. And we know the integral of x is x squared. So this thing is basically x squared divided by 2 from 0 to 2, which is 5 squared over 2 minus 0 squared over 2, which is 25/2, which is 12.5. We see that this actually works. Thank you for watching.